There's a couple of approaches to finding uncertainty. The most common is a non-intrusive method, which requires multiple iterations using a Monte Carlo sampling scheme of a basic black box solver. An intrusive method requires transformation of the governing equations. The benefit here is that you import a probability density function about each stochastic random variable, which is then propagated through the model. To create these stochastic random variables, polynomial chaos expansion allows variability in a newly defined uncertainty dimension zeta. Previously in class, we worked on a quasi-one-dimensional flow through a nozzle. We've got a subsonic flow moving through a necked area where the Mach number reaches approximately the speed of sound, or 1, at which point the flow then goes supersonic and eventually reaches a Mach number of around 3, as you can see in the analytical solution to the right. When we solved this problem, we assumed we knew exactly what the incoming pressure, velocity, and temperature was of the fluid coming into the nozzle. In reality, this is subject to measurement error, and there might be uncertainty surrounding the actual temperature, as our gauge might not be quite as accurate as we'd like it to be. Now, taking this approach, stochastic random variables were inserted where we have uncertainty about velocity, density, temperature, and pressure by default. When multiplying by a test function, integrating over the interval -1 to 1, and using the orthogonality property, we can then solve for each weight. Now, for the model run I'm about to show here, we have a standard deviation of about 10% for the incoming density, which may or may not be high. However, this is just a test case, and 5% for the incoming temperature. While the model is reaching a steady state, which looks equivalent to that of the analytical solution, you can see the uncertainty being propagated through the model about those error bars, which each represent one standard deviation away from the mean value. The standard deviation is held solid at the wall where the input uncertainty is present, and it is also set as a boundary condition. Ultimately, this would have an effect on our estimate of output velocity, would have a greater impact on our measure of density in the subsonic range, and not as much impact on our measurement of density in the supersonic range, for both density and temperature. And we also see that it has very little impact on the pressure distribution throughout the nozzle.